All right, so I just wanted to go over the notes with you guys today since I'm not here. This is for period 5. We didn't finish the example that we had. Period 6, you guys could skip ahead and start at part 3 where we're looking at reaction quotient expressions. And yeah, so we could go ahead and start here. So this is pretty much where we left off in period 5 for Chatelier's principle, and we're looking at how equilibrium is going to shift depending on different stresses that we're adding onto it. And remember a few things here. So we said yesterday that anytime you add something, the direction that it shifts is always away. Anytime you take something out, it's going to shift towards. Okay, so here if we add in ammonium here, which is over here on the left side, so the concentration of ammonium actually goes up, it's going to want to shift away from what was added. So since it's on the left side, we know that it's going to want to shift over to the right side. And when it shifts to the right, what we're essentially doing is we're producing more nitrogen and more water here. So more products are getting produced. Now, in the second part, we talked about how if you remove something, it's always going to shift towards what was removed. But there is something that I want you guys to add into your notes over here. And it's actually covered on the bottom part here where it says solids and pure liquids are never included in the equilibrium ratio. So let's kind of fit that in right here. If you have a liquid, and you know you have a liquid because it says L right here. So liquids and solids, which would be represented with the S, these guys are never included in the equilibrium expression that you have over here. So even if we're taking out the water, it actually has no impact whatsoever on the equilibrium. So the reaction shifts in no direction. So you could just say no impact or no net change. Okay. If the pressure is increased, this one's the one where it's a little bit tricky for some people. So let's review that. Anything that deals with pressure or volume, you're dealing with how many molecules you have on each side. So if we check on this side, that's 1 and 1. The coefficients are 1 each, so we have a total of 2 molecules over on the left side. Over on the right side, we have just 1 and 2, so we know that this is going to be 1 molecule here. And if we up the pressure, what the system wants to do is it wants to bring the pressure back down. And remember, to bring the pressure back down, you always go to the side with a fewer number of molecules, so it's going to shift to the right. Okay, and we can also say the opposite is true, right? If we decrease the pressure, you want to increase it to achieve the state of equilibrium that it was once at, so it's going to go to the side with more molecules, so it would shift left here. Okay, and finally, where it says increasing the temperature shifts the reaction, right? So here we have to take a look at temperature always has to do with the change in enthalpy that they give here. And I don't really care about the 45 kilojoules, but I do care about the sign. So we know that it's negative here. So this is indicative of an exothermic reaction here. And if the reaction is exothermic, it just means that heat is going to be a product. So I have heat over on the right side. Okay, so now this goes with the same principle of if you add, it goes away. If you take out, it goes towards. So when I add in the heat by increasing the temperature, right, it's going to actually want to shift away. So it's going to want to shift over to this side to reduce the heat. So we're going to shift left. Okay, and even though this one wasn't asked, you could assume the opposite too, right? If you took the temperature and you decreased it, so if we lower the temperature here, we're then going to shift it to the right side to actually produce more of the heat that was lost. All right, so looking at part 3 in our notes, we're now going to take a look at equilibrium and come up with a way to kind of have a way of quantifying what's going on here at equilibrium. And we call this the reaction quotient expression. Quotient because you'll be dividing, right? And it's an expression that gives you an idea of the concentration of products that we have, right? And you're going to compare it to the concentration of reactants that we have, okay? And another thing that's really important here is the coefficients from your equation are going to have a play in the actual equation itself. And again, that's called your reaction quotient, your QC here. Similar to what we talked about before, solids and pure liquids, which you'll know because it'll say L or S right next to the chemical that you're looking at. These guys are never included in the actual expression or the ratio itself. And it's because you're dealing with concentrations, right? And if you have a pure solid or if you have a pure liquid, there is no such thing as concentration. It's 100%, right? The whole thing is going to be that solid or the liquid. So the concentration isn't really impacted by the solid or the liquid. So it's not included inside the actual equation itself, right? And the main thing that you guys want to know here is down here. Okay, so if you're just looking at this part for the Q, right? The Q is equal to the rate of your forward reaction, which is your concentration of C to the C power, concentration of what D is to the D power. And these little exponents that you guys see here, the C and D, they come from the coefficients that you guys have in the original equation. So if that was like 3, then we'd put a 3, C to the third power. Or if if that were a 2 right there, then that would be D to the second power. So the coefficients matter in getting you the exponents right there. And then down on below, you guys have the concentration of the reactants. So we have A and B here, right? And then it's in concentration, so it's moles over liters. And again, you have a lowercase a and a lowercase b, which matches with the coefficients that you would have from the actual original equation. Okay, so we call this the reaction quotient, which is Q. Okay, and if you have a system that's at equilibrium, we actually call this setup where if you multiply the coefficients and the concentrations here to the power, you take that and you divide it by the reactants. We call that your equilibrium constant, and it's a capital K here. Okay. So let's take a look at how this connects on to chemical equilibrium. Okay, and if you have reached chemical equilibrium, right, Q and K, they have to be equal to each other. Okay, if you guys think to the example that I showed you guys yesterday with the 2 large buckets of water in front of the room, Q is at any point in time. It might have been like at the very beginning when they were first moving the water around and we hadn't achieved equilibrium yet. The K is when they've already reached equilibrium. Remember, equilibrium was a state where the rate of the forward reaction is the same as the rate of the reverse reaction. So overall, there is no change. So anytime we talk about this capital letter K, we're really dealing with once some time has passed already and everything is already at equilibrium. And the value of K or Q you get by doing all this work up here, and the constant actually means something. So if K is smaller than the number 1, right, and we're looking back here at this equation, if your K is smaller than 1, it means that you have a lot more reactants than products. Okay, why would that be? Because here on top you have your products, here on the bottom you have your reactants. So if you get a number that's less than 1, it means that you have more on the bottom. So we have more reactants here. The opposite is true, right? If your K is a number that's bigger than 1, it means that you have a lot more here than you'd have down here, so we have more products. Okay, and you could imagine if K is then equal to 1, it means you have the same amount of reactants and products, but that doesn't happen all too often. It's usually going to be smaller than 1 or bigger than 1. Okay, so we're going to go ahead and rewrite the reaction quotient for the following reactions, and because it says reaction quotient, we know that we're writing a Q expression, and again, it's really the same thing as a K expression, except we don't know whether it's at equilibrium or not. So first thing I'm going to do is I'm going to check all the phases here. If there were any solids or liquids, I'd cross them out because it doesn't matter. But these guys, we just have gases. So I'm going to go with setting up an equation just like this on top. So my Q is equal to my concentration of products. I have NO2. And my coefficient of 2 means that I just put it to the second power. And we're going to divide it by all the reactants that I have. And I only have dinitrogen tetroxide, and coefficient of 1, so nothing right there. Okay. Now on the right side here, we're going to do the exact same thing, except check out these guys. Right? We have calcium carbonate, which is a solid. Right? It's 100%, it's pure, there's no such thing as concentration for this. The whole thing is calcium carbonate. And then the calcium oxide also is a solid. Right? So we got rid of two things in the actual reaction that doesn't get included into our setup. But we're going to set up the rest. So it's products over reactants. So we have product of O2. And because of that 3, it becomes O2 to the third power. Okay? And we're going to divide it by any reactants, but I don't have anything, so it's just a 1. So our thing is just O2 to the third power. Okay, and go ahead and in the next video I'm going to go over sample problem type 1, and you guys could click on the link for that.